right, let's start with number one. We're naming the IUPAC compound, we're giving it an IUPAC name, and we've got 1, 2, 3, 4, 5 substituents. This here is all just garbage. The compound didn't load in this piece of this quiz or test, whatever. All right, so we've got 5 substituents. They're all right next to each other. 1, 2, 3, 4, 5. And that means if I go from fluorine to bromine to bromine to methyl methyl, I'm going to get 1, 2, 3, 4, 5. And you can add those up. 1 plus 2 plus 3 plus 4 plus 5. Long story short, you get 15. And if you go the other way, you're going to get 15 too. 1, 2, 3, 4, 5. It's the same thing. So we have 2 possibilities on naming this or numbering this. And so I'm going to say we should look at fluorine versus methyl. If we need to break a tie, we're going to use alphabetical priority. So we've got F versus F, M versus F, sorry, and F wins. So let's go this way. 1, 2, 3, 4, 5, and 6. So 6 is the only one without a substituent. So now I would say we've got a cyclohexane, and that's good. We've got that in the name of everything, so we don't have to worry about that. That's what we've got, cyclohexane. And then we have a 1-fluoro. We've got 2, 3 dibromo. Don't forget to throw your dibromo in there. Dibromo. Luckily, this is multiple choice, so if you forgot, they give it to you. And then we've got 4, 5 dimethyl. So just off the bat, we know we have cyclohexane in all of them. We're looking for, now we need to put them in alphabetical order. We've got bromine and we've got fluorine, we got methyl. So our bromine is going to take priority because it starts with a B. And now we're going to put these in alphabetical order. So we've got B, we've got an F, and we've got an M. So B wins, then F, then M. So we should have, let's see, we should have 2, 3 dash dibromo dash 4, 5. I'm sorry, fluorine's next, dash 1 dash fluoro dash 4, 5 dimethyl cyclohexane. All one word, couldn't fit it. So we know we have 1 fluoro, so let's see, is there anything that's just 1 fluoro? And we see B has 1 fluoro. We know we need 2, 3 dibromo. Nothing else besides B has 2, 3 dibromo. And we need 4, 5 dimethyl. Nothing but 3 has 4, 5 dimethyl. So always find your name first and then go for the multiple choice. That's my way of naming it. I name it and then I look for what I named it. If you don't see your name there, then look again. And remember that we're naming this based on the substituents. If one of these substituents had been gone, let's say this methyl, for instance, we're looking for the group of compounds. That's where we're going to start. And then we decide which way would give us the lower number total substituents if we started from bromine going this way, or if we started from fluorine going this way. In this case, we had that methyl group here, so we knew it was either going to be methyl this way or fluorine this way. We just had to figure out which one had priority, and since fluorine has the F and methyl has an M, we use fluorine as our higher priority. We could do another one of these. We could do the one where I took out a substituent, just because that may show up. So let's just take it like that. For this one, I would say I've got this group here. Do I start from bromine or fluorine? Well, if I started from bromine, I would get 1, 2, 3, 4, 5, 6. And that would give me 1 plus 2 plus 3 plus 5. If I started from fluorine, 1, 2, 3, 4, 5, I would get the same thing. 1 plus 2 plus 3 plus 5. So they're going to equal the same thing. It's going to be 11. And that means that I need something else to break the tie. So I'm going to look at, and I wouldn't start from methyl over here, whoops, because methyl is going to give me a higher number. That's going to give me 1, 2, 3, 4, 5. Now I've got 3, 4, and 5 in the mix, and that's just too high. We don't want to get a higher number. So let's look at bromine and fluorine. And bromine comes first in the alphabet, so bromine's going to win. So we're going to start it here. 1, 2, 3, 4, 5, 6. Now we can name our substituents. We've got a cyclohexane that we know. We've got 1 and 2 have bromine on them. So we're going to do dibromo. We've got fluorine with 3. So we've got 3 fluoro. And we've got 5 methyl. So same thing, we're going to rank them by alphabetical order. So bromine, fluorine, methyl, they're in alphabetical order now. So I would call this one here that we're doing, I would call it 1, 2 dibromo -3 -fluoro -5 -methyl cyclohexane. And that's just to give you an example of something he could possibly throw at you on this makeup quiz. It may not be exactly this. It could be, some little bit of different than this. But just be comfortable with figuring out where you start your numbering. Making sure you can identify that fluorine starting here is going to give you, or here is going to give you, starting at this group is going to give you lower substituents than if you start from methyl. And then always remember, if you have a tie when you're numbering, pick the one with the higher alphabetical priority. So the answer for this one was B. All right, when we go to the next one, we say, which statement below explains why cyclohexane adopts a chair conformation? Well, when we have cyclohexane, which here's a cyclohexane down here. Remember that we were talking about how cyclohexane has that steric strain because you've got your 1, 3, and 5 interactions. They're all interacting. So that's steric strain. This is the interaction between these 2 atoms, these 2 atoms, and these 2 atoms. And I showed you that on the model kit where the 3 that are sticking straight up will interact with each other. And the same happens for the 3 that stick down, wherever they are. They interact with each other as well. That's called steric strain. So cyclohexane has steric strain, but we've released, in the chair conformation, we've released its torsional strain and its angle strain. Remember that in a cyclohexane chair conformation, the angles are about 109.5, which is ideal. We've also eliminated some of that torsional, we've also eliminated the torsional strain because now we don't have eclipsing atoms. So, I encourage you to pull out your model kit here and look at this. But remember that torsional strain is the eclipsing of atoms in a ring. So we usually have, 2 things coming off here. And these 2 will be eclipsing, these 2 will be eclipsing, these 2 will be eclipsing, and these 2 will be eclipsing. These 2 will eclipse, these two will eclipse, these two will eclipse, these two will eclipse, and that goes all around the ring. When we put it in a chair conformation, we've now put the hydrogens or the other groups that are connected to the main ring, they're now not eclipsing each other. And that's why we get those axial and equatorial positions. They're not going to eclipse each other. The axial will stand up, the equatorial will stand straight. Now they're sort of perpendicular to each other, and so they're not they're not having that eclipsing interaction. And that's what torsional strain is. So we can say torsional, I don't know if I'm spelling it right. No. Torsional strain has been decreased. So we've got a good angle strains. We've got like no angle strain. So we can say that angle strain has been decreased and that torsional strain has been decreased. So this is just knowing what a chair conformation tells us. And so now we're just looking for the right thing. So the conformation has decreased torsional strain. That's good. And increased angle strain. That's not good. The conformation has increased torsional strain. That's not good. The next one also says increased torsional strain. I can get rid of it. So those three are wrong. But it has decreased angle strain. That's right. This one says increased angle strain. That can't be right. This one, the conformation has decreased torsional strain and decreased angle strain. That's good. That's the one we want. That's just remembering that the chair conformation has reduced two strains, angle and torsional. It still has some steric. So, there's still some strain, but it's not angle or torsional. Okay. Which statement is true about the molecule shown below after the ring flip? All right, go ahead and number your carbon. And remember, we like to look for a little group. That's what I like to do, and say, okay, my number 1 should be around here. For this purpose, it doesn't matter too much. I just want to make sure that I'm numbering it the same as if I drew the chair conformation again and flipped my ring. I don't necessarily have to, though, because I can say, okay, I've got a bromine on 1, a fluorine on 2, and they want to know how the 2 fluorine atoms are related and what the bromine atom will do. So let's take the 2 fluorine atoms instead, and I've got a 2 and a 5. So I've got 2, 5 fluorine. This is the same as a 1, 4 or a 1, 5 because it's something even and something odd, or something odd and something even. That's what that rule is. It's not 1, 3, 5 basically. So they're not going to be a 1, 3, 5 interaction. They're a 2 and a 5. And you could have numbered this differently. This could have been 1, this could have been 1, 2, or I'm sorry, 1, 2, 3, 4, 5, 6, and that may make it more like what we're used to seeing. So I'll just do it like that. So 1, 2, 3, 4, 5, 6. So now we have fluorine on the 1 and the 4, and since we're used to that, we'll go with that one. So we have a 1,4 interaction, and they are both axial. So they're the same. And we know that if 1 and 4 are the same, they can't be cis. They have to be trans. Because remember, if 1, 3, and 5 cis is the same, then the 1, 3, 4 or the 1, 4 cis has to be different. You can't have them be the same. 1 and 4 can't have the same orientations as cis 1, 3, 5 if they're both cis. So that's how I kind of remember it. Make sure I'm on the right page there. You can write this out when you get your test if you want to. Just write down, I would write down something like 1, 3, 5 cis equals same, 1, 4 cis equals different. And then I can go back and go, okay, well, if 135 cis is the same, 135 trans has to be different, and 134 trans has to be the same. So since we have 1,4 and they're both axial, they're the same. They can't be cis, they have to be trans. So these are trans. So now you can go through your answers and say, okay, the two fluorine atoms will be trans to each other. Yes. The two fluorine atoms will be trans to each other. Yes. I can get rid of C and D. They don't mean anything to me because they can't be cis because they're the same. So now we're looking at the bromine. What happens to the bromine when you do a ring flip? And we should remember that whenever we flip something, it's going to take on the opposite orientation of its current position. So now we should get that bromine, it was axial, it's going to flip, it should be equatorial. So now we can say that one says axial, that one says equatorial, this one's wrong, it can't be A, it must be B. And that's because the two fluorine atoms are trans to each other and the bromine atoms will be equatorial. Also, you could look at, get rid of some of this. You could look at the bromine and the fluorine atom. This is a 3 and a 1 and a 3, and you can say, well, those look like they are 1, 3. They're on the same, they're both axial. That's the same. 1, 3, and 5 have the same thing. That must be cis. Then you can move over to this fluorine atom and say this is 3 and 4. 3 and 4, they're the same as well. They're both axial. Well, if they're the same and they're one even, one odd, then they must be trans. And so you could talk about all of these in relationship to each other. You could say that these two, 1 and 3, they're cis to each other. You could say fluorine here and here, bromine and fluorine here, they're the same, they have the same orientation. They're both axial, but one's on a 4 and one's on a 3. Well, these have to be trans. And then we could say the two fluorine atoms, they have the same relationship as this bromine and this fluorine do. So fluorine has the same relationship as that bromine fluorine, and they're trans. These two are trans too. So you could go around and look at all of those options as possibilities. I don't think he'll ask, I mean, he could ask that. He could ask what the relationship between, and he could circle one. Or more likely, he would just change this atom to something else, like chlorine, and then ask you about what the relationship between bromine and chlorine is, or fluorine and chlorine, and that way he could ask you more things about it. That's just one way he could change this question up. Okay. Which of the structures below represents trans 1 isopropyl 4 methyl cyclohexane? So here they tell us that it's trans, it's 1 and 4, and we've got an isopropyl and a methyl on a cyclohexane. So we see our chair conformation. The first thing I want to go ahead and do is number these. Now, from the jump, we can see we have isopropyl and methyl. Isopropyl is bigger than methyl because it's got more stuff going on, and methyl is just the line. So we want to give, when we're numbering our answers here, we want to give this isopropyl number 1, and we want to give methyl number 4. So let's start on each of these at the isopropyl. So we're going to start here. 1, 2, 3, 4, 5, 6. I'm going to zoom in because they're really small. 1, 2, 3, 4, 5, 6. Okay, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. All right. Now, could you have numbered these the other way? Let's see. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. You could. It wouldn't really matter. You should still get 4. 1 and 4 are far enough away that they should give you the same thing if you number it. Either way, you could go this way around the carbon ring. You could go this way. But let's look at letter A. We've got our isopropyl on 1 and our methyl on 5, and this says that we want it to be on 4. So that can't be right. It's on 5. And the same with B. We've got 1, 2, 3, 4, 5. That's not 4. That's 5. So B can't be right either. And just to show you, you could name it the other way. I'll name it the other, or I'll number it the other way too. So we could say 1, 2, 3, 4, 5, 6. And I'll do the same thing here just to show that we could number it either way. That we'll get the right answer. It's because it's on 4. And so you can see now it's on 3, and that still isn't what we want. We want it on 4. We don't want it on 5 or 3. So those can't be right. They just can't. So they're out. So let's look at C and D now. We've got a 1,4 relationship, and they're trans. So we just did that up here on this problem. 1, 4, trans equals same, right? We just said that up here. 3, 4 axial, same, trans. So this we should have the same. We should have either both axial or both equatorial. So let's look at D first. D, we have our methyl group. It's on the equatorial position. That looks good. But our 4 group is on the axial position, and that's not the same. Those are different. On C, we've got our isopropyl group equatorial and our methyl group equatorial. Those are the same, and they're in the most stable conformation, so it must be C. All right, next we've got which of the chair conformations matches the structure below? Okay, well, we've got our, we can number these. So again, I'm going to look for a group of substituents. Here we've got 2 methyls, so that looks pretty good. I'm not going to number it this way because those are really far apart. I'm definitely not going to number it this way because those are really far apart. So I want to start here. And if I go to the left, then I've only got 1 carbon in between. If I go to the right from this methyl here, if I go to the right, I've got 2 carbons before I get to my next substituent. So I want to go this way, which means I'm going to start at this methyl as 1, this methyl as 2, this 3, this one is 4, 5, and 6. And you can look at that and say, does that make sense? Yes, it does. Now, the reason that I number it like this and not just ambiguously is because I want to make sure that I get my numbering right on each of these chair conformations, and they all should have some group of 2 things together. And so that's where I'm going to start. And then I want to make it to where it goes the right way around my carbon ring every time. It should go to the left. And that way I'm being consistent. And I'm not going to get a different numbering system for one of them than the other. So I'm going to start here. 1, 2, 3, 4, 5. I'm going to zoom in again. 1, 2, 3, 4, 5, 6. What did I forget? 6. Yeah. And remember that I've started at this one because I'm going to move to the left, and I only want there to be one carbon without any substituents on it between 2 and 4, because that's what I have, 2 and 4. And so that works. That's the way I want to go. All right, this one is 1, 2, 3, 4, 5, 6. And 1, 2, 3, 4, 5, 6. So whichever way you name the first, this one here, that's how you should name all of them. And so now we can see they're all numbered the same way. There's no ambiguity in terms of what carbon is what. And now we can look at this and decide what's going on. So we want a substituent on 1, 2, and 4. So let's see, 1, 2, and 4, that looks good. 1, 2, and 4, that looks good. 1, 2, 5, that's not good. And 1, 2, 5, that's not good. 1, 2, 3, 4. I guess you could number it the other way and get to 4, but then we would have numbered them all differently. And I'm trying to make sure that they're all numbered the same. So I'm going to mark these off. I don't think these are right because they have a substituent on 5, and I don't want a substituent on 5. All right, so now I'm going to determine what the relationships are here. So I've got two methyls that are cis to each other, and we know that because they are on wedges. So that means they're cis, and they're on the 1 and 2. So a cis 1, 2 is going to have, so cis 1, 2 is going to have different positions in terms of axial and equatorial. So I'm just going to look at my 1, 2 for now. 1 and 2, these are different, so that looks good. These are the same. They're both equatorial. This one has an equatorial and this one has an axial. So that looks good to me. I like that one so far. But just to make sure, I'm going to check my 1, 4 or 2, 4 relationship. Let's go with 1 and 4. I'm more familiar with that relationship. So 2 and 4, 1 and 4, 1, 4, they're trans to each other. Trans, because one's dashed and one's wedged. So this means that if they're 1, 4 and they're trans, they've got to be the same. So now I'm only looking at 1 and 4. And this one has two equatorial positions. So again, I like this one. This one looks good. This one also has 2 equatorial positions. But that 2 is what is really killing this answer for me, because the 2 is not in the right position here. So I don't really like B. I'm going to go with A because 2 is sticking up. And you could check that by saying 2 and 4. And this is just, I'll put this up here. 1, 4. These are trans. They have to be the same. 2 and 4 relationships are just like 1 and 3 relationships. And so if you had a 1, 3 relationship, or a 2, 4 in this case, we'll put 2, 4. And they're trans. They'd have to be, let's see, 1, 3, 5 trans is different. And so that makes sense. We're now looking at these two. And so we can look at 2 and 4. 2 and 4 are different. 2 and 4 here are not different on B. So again, I like, I don't want to erase that. I like A. A is my answer. Okay. Which of the compounds below would have the highest heat of combustion per mole of substance? Well, I'm going to look at this and instantly go with B, because remember, this has the most strain. It's gonna release the most energy when it is combusted. It's gonna release the most energy. A can't be right because it's very stable. This is a stable compound, and so we wouldn't imagine that this was going to give us a high energy when broken or when combusted. So I know it's not A. And if A is the biggest out of all 4 of these, and A has the least, then I know it can't be D or C. I'm going to go with the smallest. If he asked you for the lowest heat of combustion, then it would be A. But we're asked for the highest, so it's going to be B. And that's just something you should recognize and just try to remember and just be quick. That the smaller, the more compact, because remember, this has a lot of angle strain and torsional strain, and it's going to have a lot of tension going on. It's really strained, so it's going to have the highest. So just that's something you just need to remember, I think. Okay, how are two compounds below related? Well, we have two chiral centers, it looks like, and one is changed. And I just want to make sure. Oh, but wait a second. These two are in different places. So I'm going to number my ring. I'm going to number my carbon chain. That's my first move if I'm unsure. So I've got a 1, a 2, a 3, a 4, a 5, and a 6. And then I started where the bromine's my first substituent. So I'm going to start from here this time. 3, 4, 5, and 6. And so now I've got bromine on 3. Okay. That's good. Methyl's on 4. That's good. All right. And 1 has been changed. I'm going to say they're diastereomers and make it D. And I've got my little cheat sheet here. Just want to make sure I'm giving you the right answer there. That's number 7. Yep. So those are diastereomers. All right. What is the configuration of the chirality center in the compound shown below? Well, we've got two chirality centers. We've got one, I'm going to zoom in on it. One is here and one is here. Right? Let's start with the one here first. And if it helps to redraw it, then do that. But let's just look at what we've got. We've got a methyl here, right here. And so we know that if methyl's present, it's going to be our number 4. And chlorine's present, so it's got to be number 1. And then we can go out from these two carbons. So we're going to look at this carbon and this carbon. They're both CHH. And so then we have to move on to the next ones. Now we're here and here. This one is HHH. And this one is CHH. So this one should win. So we should have a 2. We get a different color. So we have 4, 1, 2, and 3. That's 1, 2, 3. This looks S, but our number 4 group is in the back. The front. So it's actually R. So we got 1 R so far. I'm going to erase some of this just so I can look at my other chirality center more easily. So our other chirality center is here. And we can look at our carbons. So we've got 1 carbon here, 1 carbon here, 1 carbon here, and our hydrogen's in the back this time. That's not drawn correctly. Here we go. So we can really just ignore our hydrogen. It's in the back. It's not going to bother us. All right. So my first carbon, let's say here, is CHH because it's attached to 2 hydrogens and then 1 carbon over here. Our carbon up here is going to be, it's got 1, 2, and an H. That's going to be CCH. Our carbon here is attached to a carbon and then another carbon, CC, and then 1 hydrogen, CCH. That's because I counted both of those double bonds as a carbon. So now I have a tie between this one and this one. So I need to move outwards. And so I'm going to pick a carbon. I'll use pink here. I'm going to pick a carbon here and say this carbon is C. Let's see, what is it? It's CHH, or it's HHH. And then this carbon here is, now it's C, C, H, C, C, H. So this should get the 2 spot. Okay, sorry. This should get, I'm sorry, this should get the 1 spot. 1, 2, 3. 1, 2, 3. This looks S, and it is S. So we have 1 R and 1 S. And if that was like too messy and confusing, remember you can always draw them out by themselves. So for this one, we would have had, and there was one on a wedge, that's this one. Remember our hydrogen was in the back here. I didn't draw it in because I know it's in the back, so it doesn't really affect anything. And then, you can move out as you count, and that'll help. I mean, you can say, okay, I'm just comparing these 3 carbons. That's 1, 2, 3. They're all carbons. What's attached to them? Well, let's see. The one over here has this attached. So that's going to be carbon, and then it has 2 hydrogens. If you can't visualize the hydrogens, just draw them in. So now I've got this one as being connected to a carbon and 2 hydrogens. That's CHH. This one over here is connected to a double bond. So that means that I've got 2 carbons over here, and then there's still a hydrogen on it. So now I need to look at it as this carbon is got 1, 2 C's and an H. Then if you come up to this top carbon, we say, okay, this one's got 2 attached to it. So this one is C, C, because we're talking about these 2 C's, and then there's an H. There is an H attached in here somewhere, because it's got to have 4 things attached to it. And so that's how I would work this 1 carbon at a time. And then now that I see I have this tie here, I can really get rid of all of this stuff. This one is going to be, this is going to be the last one. It's going to be 3. I now know that. So 3 is here. Now I'm just going to look at, I'm going to get rid of hydrogen because I know it's 4 and it's in the back, so I don't need it. Now I'm just going to look at these 2. When you get to a terminal one, like here, and you don't have anywhere else to go out, then you're just going to kind of go back. So now we're going to say I'm at this end. There's 1 carbon here. I'm looking at this carbon, and I'm moving backwards. So now I'm going to say there's 1 carbon here, and there's 1 carbon here, and there's also a hydrogen over here, not there. 1, 2, yeah, 3. There's actually 2 hydrogens, but we're just going to count one of them. Yeah. For this one, we've moved out to one of these. It could be either one of them, and we can say that there's 3 hydrogens coming off of these. And so this carbon now is H, H, H. It loses to this one, which I didn't write out. Here it is. C, C, H. It loses to that. So that's another way to like do it just 1 carbon at a time. Anyway, the answer is C. All right, which of the following is a Newman projection of the compound shown below? Okay, I do this kind of weird, but it works, I think. So let's see. So we have what looks like a meso compound maybe, because we can twist this. Remember, we can twist this side of the molecule, and it'll be the same, and then I'd have a symmetrical thing. So let's just look first at what we've got. Remember, I do my Newman projections where I kind of draw this like imaginary plane in the middle, and then I say all of the things on this side are backward or towards the back, and all of the things on this side are towards the front. Not sure if that works for anybody else, but if it does, good. If it doesn't, we'll see. We'll see what we can do. So then I just draw these. I just draw these out. I go, okay, well, bromine's in the back. Bromine, it's also sticking up. And then, let's see, methyl's up. Hydrogen's, oh, wait a second. Let me get rid of that. Nope. Methyl is down. This line got me confused. Let me erase my symmetry line. Okay. Methyl is down and hydrogen is out. That means carbon, and I'm going to put hydrogen more this way. Let me start over. I need more space. Okay, let me draw them up here. Okay, so we've got bromine. This is, oh, that's because I'm drawing the back carbon first. Always draw the front carbon first. Bromine is in the back. We've got hydrogen in the front. We got methyl sticking up. That means our bond between carbon must be going this way. Then we've got bromine going up. We've got hydrogen coming out, and we've got methyl going down. Okay, that makes more sense. Okay, so can I rotate this to get it to be like this one? It looks like I can. It looks like I can draw the bromine here, change this to hydrogen, and then move these two, because remember, I want to get the same compound. I've got to do a couple of swaps. So this would now be H, and this would be methyl. So that looks like it could work. And I could do the same thing over here, bromine, hydrogen, hydrogen, methyl. I'm just swapping compounds. That's all I'm doing. And so that would give me the same orientation. So that would look good. I haven't changed the molecule. I've just moved things around. Remember that whole swap thing. If you swap twice, you have the same compound. If you swap once, then you've got different compounds. You've got the enantiomer. That's basically what I'm doing here. But I also want to look at my other answers just to make sure that I'm not missing something that's really silly. Like the fact that this one here has 2 bromines on the front carbon, and this one also has 2 hydrogens on the back carbon, and that's just not true. Because remember, we're looking at this carbon here and this carbon here, and we're looking down this bond. And so this one just cannot be right. Here I've got a bromine and a hydrogen and a bromine. This one I'm going to look at a little bit harder. Okay, the other thing we can do, and this is I think how I solved this one, is after I kind of like stumbled about these for a couple of minutes, I said, well, let me figure out what the RS, the absolute configuration is, and then I can figure out if my absolute configurations on these are correct. All right, so let's do that. That's much easier, I think, actually. All right, so bromine's going to have a 1. That's good, because remember, these are chiral centers. Woohoo for chirality. Okay, so these are chiral centers. So we've got 1 on bromine. We know that this methyl group is going to be 3 because there's a hydrogen back here somewhere. And if hydrogen's in the back, we don't need to worry about it. It could just not be there, really. Okay, and then that means that if that's 1, this has to be 2. So that was easy enough. And we have hydrogen in the back, so we are going to get whatever we get. This looks like R. It is R, so that's good. Let's look at our other one. Put the R here. We have an R. And then I'll do it in blue for the other one. So again, we've got bromine is 1. This is 3. This has to be 2 over here. Well, my pen would work. And we've got 1, 2, 3. Hydrogen is still in the back in this one because bromine's in the front. So hydrogen's got to be in the back. 1, 2, 3. This looks R. It's got to be R. So now we're looking for that rotation. Well, I can erase this and draw it again just the way it's written. Or I can look at this and try to figure it out. Let's just draw our chiral things. So we've got 1. Whoops. We got 1, 2, 3. Hydrogen's in the front here, bromine's in the back, carbon's in the plane. That carbon group, remember that's R. I'm just drawing the front chiral center right now. The back chiral center would have bromine up here. It would have hydrogen back here, or forward rather, and it would have methyl coming down. And that R group has to meet up with that other R group over there because remember these lines connect in our sawhorse conformation or whatever you call it. All right, now I'm going to give these chirality. So I've got 1. I don't have to think about this. I've already done it. 1, 2, 3. And then this R group is 2. Hydrogen's in the front this time, so that's going to give us a little bit of a problem, but we're going to go around 1, 2, 3. This looks like it is S, but that means it's actually R because H is in the front. All right, H is in the front again here, so we have to be careful. We've got 1, 2, 3. 1, 2, 3. This looks S again, but this is R. So that's good. We've got the same configuration. So this one, for now, looks like the one I want to pick. But let's look at the other ones just to make sure. Okay. And you can try to do this a little bit quicker if you can remember which way these carbon things come out, but maybe a little confusing, so I won't go into that. But let's just draw these. So we've got 1, 2, 3. Remember, I always make these on hashes, dashes, and these on wedges. That's just my way of doing it because it makes it easier in my brain to draw the sawhorse. So that means I'm going to have this here. A hydrogen coming back, that's good. A bromine coming forward. And then that means my R group has to go back. There's my R group. And then I've got my bromine coming back here. Hydrogen's coming forward. And methyl is going down. And my R group has to come this way because they're going to connect, remember. They're connecting. So now I can use my configurations. Remember that methyl is always going to be 3 when hydrogen's present. Hydrogen's in the back this time. That's good. Bromine's number 1, and our R group must be 2. So that's 1, 2, 3. Hydrogen's in the back. This looks S. It is S. This one over here, we've got bromine. We've got 3 for the methyl, 2 here. Hydrogen's in the front this time, so we need to be careful. We've got 1, 2, 3. It looks S, but that means it's actually R because hydrogen's in the front. So this one can't be right. Let's just look at this last one really quickly, make sure we're not missing something important. Out of space, I'm going to erase this. Okay. So we got, remember, I like to put these on dashes and these on wedges. Okay, so now we've got my front carbon, hydrogen's in the back, methyl's up, bromine's in the front, and that R group must be coming backwards, or towards, in the plane, but towards the right. Okay, and this is bromine. Okay, and then on my other one, my back carbon, I've got hydrogen in the back. That's good. I've got bromine coming forward, and I've got a methyl coming down. That means my R group must be coming out towards the left. And so I am going to now give these priorities. So again, they're all the same. 1, 2, 3. H is in the back. That's good. This looks like S. So it is S. Let's do this one. 1, 2, 3. 1, 2, 3. H is in the back. This looks S. It is S. So this can't be right either. So that's how I would go about this. I would do my chirality centers for the molecule given, and then I would go through and draw out my chiral centers, taking the front carbon first and then taking the back carbon and just attaching it to it, making sure that the R groups are ending up in the same place because those R groups are really shared. Those R groups represent each other. So that's how I think of that. Okay, so this one, the answer was A. Which of the following compounds is meso? Well, here's another chiral thing. And look, it's the same compounds, pretty sure. Let me erase all of my scribble scratch so we can look at them. But I'm pretty sure it's the same compounds. Like we've got Br, Br, H, H, Br, Br, H, H, Br, H, H, Br. Yep, that's the same, and these are the same. So we've got all the same things. So let's go undo my chicken scratch and let's look at what I should have written in what I said these were. Maybe I can go back enough to find out. But look, this one's SS, so this is S, S. Can't be that because they have to cancel out. And it can't be A because A is RR. So it's got to be one of these. And remember, we said this one's definitely not it. Or no, not that one. We said C is definitely not it because we've got 2 bromines and 2 hydrogens on the same carbon. So these aren't even chiral, not chiral. Because we're looking at this front carbon here. And if it's got 2 of the same groups, it's not chiral. And the back carbon here, we've got 2 hydrogens, and that can't be chiral. So this one isn't meso, it's not chiral even. So that means it's got to be B. That's meso. I'm pretty sure this one was, let's see, I believe this one was SR. And that's good. That has a symmetrical thing. We've got a bromine on each side and a hydrogen on each side, and it's coming up with 2 different absolute configurations. So it's got to be B. And we already figured that out from the question before, so we saved some time by going through them all. All right, how many optical active compounds are shown? Well, remember that we can cut through an atom to find our line of symmetry. So I'm going to cut right through that trans methyl, and now I've got 1 methyl here, 1 methyl here. That looks symmetrical to me. I'm going to say this one is. I can also cut right through this one, right through that atom, and now I've got a symmetrical thing. I've got 1 here and 1 here. That looks good to me. Here, though, if I cut through this atom, I'm left with a trans and a cis, and I know that can't be right because they've got to be cis to each other. So these 2 are meso, and this one's not meso. So that means there's only 1. The answer is B. The answer is B here too. Yeah. And if you cut anywhere else in this molecule, it doesn't give you symmetry. It just doesn't happen. All right, identify the true statement below. All right, so first, before I even to look at this stuff, I just look at the answers and I try to figure out what's happening here. What are they asking me? So they're asking me about compounds 1 and 2, and all of these, 1, 2, 1, 2, 1, 2. And then they're asking me about 1 and 3. So I don't even have to compare 2 and 3. I'll never have to compare those. So that's good. I'm just looking at 1 and 2, and then 2, and then 1 and 3. So I'm first going to just look at 1 and 2 and say, okay. And what are they asking me? They're asking me, are they diastereomers or are they identical? All right, well, let's say we've got a chlorine on a wedge here, and we have methyl on a dash. Well, here we have chlorine on a wedge and methyl on a dash. And they may look different because they've switched the chlorine position. They haven't done anything to it. They've just literally switched which one is sticking out and which one's sticking sort of up. So they've literally done nothing. These are identical compounds. That methyl that's right here is still on a dash over here. And that chlorine is still on a wedge. And the rest of them haven't changed. Nothing's changed. So these are identical. So now I'm going to go down here and I'm going to take out all the ones that say that they're diastereomers because they're not. That means C is out and A is out. Okay? That means I'm left with D and B. All right, so now let's look at 1 and 3. Now they want to know if they're enantiomers or diastereomers. Okay. 1 and 3. Now remember, swaps. That's what I was doing earlier. swaps. When we have an even number of swaps, it's the same. When we have an odd number, it's different. It's the enantiomer. Enantiomer, however you spell. I'm not a good speller. Okay. And that means that if you swap it once, you'll get the enantiomer, and if you swap it twice, you'll get the same compound. And that's for one chirality center, but it's going to apply here because if we only change, well, we're looking at enantiomers and diastereomers. So, but let's just look. Remember, if we change all of them, it would be an enantiomer in a diastereomer case. So let's do that. When you're asked about more than one chiral center, let's just do this, greater than one chiral centers. Then we're going to look at how many things have changed. Has one thing changed, or can we say some, not all, or all? And remember, some, not all is the diastery, and all is the enantiomer. I literally cannot spell to save my life. Enantiomer, whatever. Okay, so let's look at 1 and 3. We've still got that chlorine on a wedge and that methyl on a dash. So this one hasn't changed. But this one has, yeah. So 1 is changed. That means some, but not all. So I would say these are diastereomers, and I would go with D. Yes. Okay. All right, how many chirality centers are shown in the compound below, and what are their configurations? All right, so we're looking at, let's start from let's just go like this, just move down the molecule. So we've got 1, 2, 3 methyl groups. None of those are good. We're going to just cross them all out. And that means that this is also out because it's attached to 3 of the same groups. So that's not going to be a chiral center. Here we have silicone, and it's got 1, 2, 3, 4 groups attached to it. And remember, we said that there's silicone, sulfur, oxygen, no, nitrogen, and phosphorus, I believe, can all be chiral centers. So this is a chiral center. Oxygen, no, because look, it's got 2 lone pairs, and there's only 2 things attached to it, so that can't be a chiral center. Even if we were thinking, oh, maybe oxygen could be, it can't be. And then we have this chlorine, which has a methyl group here. That's 1. Here's a chlorine, here's an oxygen, and here's a carbon. That's a chiral center. So that's good. I'll put a little star next to this one. And then here's a double bond, so we can't have a chiral center there. So it looks like we just have 2. Now I have to figure out what their configurations are. So let me erase all my scribble scratch. And then we're going to see that we've got a carbon, a carbon, a hydrogen, and a carbon. So now we have 3 carbons. This one's obviously 4. It's in the front, so we need to be careful. This carbon here is attached to 3 carbons. So we've got C, C, C. This carbon here is attached to an oxygen and 2 hydrogens. Remember, those hydrogens, we can't see them, but they exist. And then this carbon here is attached to 3 hydrogens. Remember, methyl's always going to be number 3 if hydrogen's there. And then we have an oxygen, which beats carbon. So we can say that this is 2. Let me get rid of that. I'm sorry, this is 1, and this is 2. So 1, 2, 3. It looks S, but hydrogen's in the front, so it's got to be R. And now I'm going to look at this other chiral center. I'll erase some of my scribble scratch here so we can see better. All right, that's our chiral center. We're looking at carbon, we're looking at chlorine versus oxygen here. And chlorine's going to win. So this is going to be 1, but this has to be 2. This oxygen is, we're also looking at carbon and carbon here. So oxygen must be 2. Remember, methyl is always going to be lowest priority. So that's going to be 4. That means this has to be 3. We get 1, 2, 3. Hydrogen, or our group 4 is in the back. This looks S. No, this looks R, right? R. Yeah, this looks R, is R. Whoops. Looks R, it is R, this is R. So we have 2 chirality centers. They are both R. That's A. Okay. Identify the true statement below. A pair of enantiomers will have the same boiling point, and each molecule will rotate plane polarized light in equally opposite directions. Well, we know that enantiomers are really hard to separate, and so they will have the same boiling point. The only thing that's different about them is that they do rotate plane polarized light in exactly the opposite directions. So far A is my favorite, but I'm going to go through them and just read them. I know they have the same boiling point, so I'm going to cross out anything with different boiling points. And I know that they rotate light in opposite directions. So if D has that they rotate light in equally the same direction, I know that can't be right. So the obvious answer here is A. And that's just knowing what enantiomer's properties are. What type of reaction is shown below? Well, we've got an iodine attached to we have an alkyl halide, and we have OH. What happens? OH goes and like attaches to that alkane. So I would call this a substitution because your OH is now attached here and your iodine has swapped places with it. So that's just a simple substitution. Which statement is true about the reaction? All right, well, we've got the same reaction here. And remember that if there's a negative charge on something, it's most likely going to be a nucleophile. And I remember I write this out. I go, nucleophile. I go, it wants to be near positive stuff. So that means it's going to be a negative charge, right? An electrophile, electrophile. I probably start with electrophile because it's easier for me to remember. I go, it wants electrons really bad, so it's going to need to have a positive charge because positive wants something negative. Positive attracts negative, so it's got to be that. So now I see that and I go, okay, if there's something negative happening, that's going to be my nucleophile. Okay, so this is a nucleophile. Um, that means if that's my nucleophile, this has to be my electrophile. And remember that he said that alkyl halides will most of the time act as an electrophile. So now I can say, okay, hydroxide is the electrophile? No. Hydroxide electrophile? No. So A and C are out. And then I say, okay, I looked at this one for a while because I was like, what? But just, they're both the same in the front. Look at the back. Okay. Iodiethane is a nucleophile? No, it's an electrophile. So it's got to be D. Okay, what type of reaction is shown below? All right, let's see what's happening here. We have 2 products. We end up with 3 products, and we've eliminated something off of this one. We have removed iodine from that, and now it's in our products as a single thing. It's got to be an elimination because we literally took it off of that. We took it out of this reactant and we made it a product here. We've added something to our product side. That's got to be an elimination. Which atom is most polarizable? For this one, you have to remember that the further down the elements you go, the more polarizable they become. So this is just literally looking at the periodic table and saying which one is lowest in the halogen group. It's iodine. Which atom or molecule below is likely to act as an electrophile? Well, here we're just going to draw in um, our signs, right? So chlorine is going to probably have a more negative sign. So is oxygen. Um, and that means that if those two have that negative sign, this B has to have a positive sign. And remember, as before, we said that the electric, what are they asking us for, first of all? The electrophilic site. We said electrophilic needs to have that positive sign. So we've already drawn two negatives, which means that would be hard to pick from two negatives. So we know that this B site must be the electrophile because it's got that positive charge. And that makes sense because chlorine and oxygen are both pulling electrons towards them. So it's going to adopt this positive charge. What organic product is obtained from the mechanism shown below? Okay, well, we're just simply going to follow our arrows. We can't do anything. We can't do anything more or less than follow the arrows. So the first thing I notice is that this negative is moving towards this CH3. That means, and the bromine's leaving. So that means I've got to have some bromine as a product, but it's on its own. It's completely its own thing. So I'm going to put a line there as to say that it might not even be shown because remember, we only show the organic products. And just off the bat, looking at that, I go, okay, well, if that is the case, and all of these give me bromine as a part, as something that's attaching to my molecule, I don't think any of these are right. This is the only one that looks right to me because bromine isn't in it at all. Bromine took electrons and left. So bromine said it was going to do. It's like, I'm getting out of here. But let me just look at that. Let me just, make sure. So we know that this negative is going to get that CH. And so bromine took electrons with it. That means that this should connect to this. And so here they have it connected with the bromine, which that can't be because bromine took its electrons and left. And here they don't have it connected at all. So that can't be right. So this is the only one that has it connected. And bromine's the leaving group. It said, bye. Okay. So this is the only correct answer that there can be. See. And again, that's just reading the arrows, knowing that if bromine takes its own electrons, it's gotta go. Bromine gets that negative charge and it takes off in its little bubble. It's a little rocket. And that means that if C is left with some deficiency, it's going to attach to where that arrow is pulling it to. So again, um, we've got D as the answer. Which of the following compounds cannot act as a nucleophile? Well, remember, nucleophiles, they want a negative charge. So this one is just recognizing that boron is just unhappy all the time. Boron has CH3, and the only thing it's going to do is it's got an empty orbital, which means that it's willing to, what is it willing to do? Is it willing to take electrons? Yeah, it's an electrophile. It's willing to take some electrons on, but it doesn't have anything to give away. It doesn't have any electrons to to give to something positive, to get something positive to attract to it. And that's just knowing boron's in the third group, the 13 elements. There are the 13th group elements, and that means it only has three valence electrons. And it's using all three of those to bond to methyl three times. And boron's just always unhappy. It's an unhappy element because It's got three bonds, that's good, but it doesn't have a full octet, and so it's mad about that. But as soon as it takes on electrons, now it's got a negative charge, and it's upset about that. So this is just remembering that boron's kind of unhappy. If boron's an answer here as a nucleophile, it's the answer because it's just miserable. And just remember H2O, you have H2O. You've got H here, and then two lone pairs. So this is going to totally be willing to take on some positivity. You know, it's going to give away electrons pretty easily. Anything with lone pairs usually will be able to act as a nucleophile. pH3, P 1, 2, 3. It's got a lone pair. It's like nitrogen. 1, 2, 3, 4, 5. This is good. It'll totally donate to it's a nucleophile. It's got that negative charge on it. And nitrogen is just like phosphorus. It's got those lone pairs. So it's going to do the same thing. So boron's the only answer here. And that's just because it's unhappy. It's never going to be able to give electrons away, especially if it's bonded to three things. So that one's B. What is the major product obtained from the addition reaction of HBr with ethylene? Okay, so we've got ethylene. It looks like, let's see, major product obtained from the addition of with ethylene. So ethylene's got a double bond somewhere, and ethyl is 2. So 1, 2. And it looks like that. And we're adding bromine. I'm sorry, we're adding HBr. So bromine's going to take those electrons. This is going to attack that hydrogen. That means we're going to get a positive on one side. So we'll get plus, and we'll get negative. So this will be plus bromine negative. That bromine is going to attack that positive side, and that's going to give us a little bromine kick. So it should be A. Okay, and then we've got which statement must be true about the reaction with KEQ? Okay, KEQ is less than 1. Remember I said K, well, give me my pen, K, okay. Remember I said KEQ if the arrow's pointing towards the KEQ. That means he is entering the system. My KEQ, I look at it as my system. So he's entering my system. That means that this is a endothermic reaction or endogonic reaction. So let's see what my answers say. This reaction is exergonic. Well, that ain't right. The reaction favors products over reactants at equilibrium. No, because the reaction is going to move to the left as well. The reaction is going to go in the same direction as my arrow is going. So that's not right. But we know that when you have an endergonic relation or a reaction, you have something that's endothermic as well. This is also endothermic. And that means delta H is positive, and we said that we can pretty much say that delta H is equal to delta G. And if delta H is positive, that means that delta G must also be greater than 1 or 0. And so that has to be B. And delta S, I'm not even going to worry about delta S. All right, which of the following is the strongest electrophile? All right, well, let's go back up to my little note up here. Electrophiles want positive charge. So I'm going to look and see, does anything have a positive charge? Yes, A does. That's automatically the answer. Which statement is true about the reaction below? Okay. So let's go back up to my little note here. Electrophile, nucleophile. All right, so it looks like this is going to be, I didn't even like read my note. It's got the negative, so it's going to be my nucleophile, right? Nucleophile. That means this has to be my electrophile. And let's see what's happening. OH on the product side has gained a hydrogen. That means that it must have been acting, it's accepted a hydrogen. Let me put it that way better. It's accepted an H plus, a proton. That means it has to be acting as a base, because bases will accept um, bases accept hydrogens. Acids give them away. This is the Bronsted-Lowry definition. Not to be confused with Lewis. Lewis says that bases donate electrons and acids accept electrons. We're talking here about hydrogen protons. So this OH accepted a proton from the ion here, whatever you want to call it. So I'm going to look, and it says we said it's acting as a base. So I'm going to look here and go, hydroxide is acting as an acid. That can't be right. That can't be right. So it's got to be between entropy increasing and entropy decreasing. I got this one wrong because I wasn't sure about this entropy increasing or decreasing. You've created more products, so maybe, and you've given, I don't know. The answer is B. Um, and I'm gonna have to look into this a little bit more. I'm not 100% sure on how you know the entropy is increasing, but I'll look this up and then I'll come back and tell you. And he may say it in his video. I haven't watched his video yet. But that was a 50-50 chance. So there you go. How many transition states and intermediates are present in this free energy diagram? All right, well, we've got two transition states right here and right here. We've only got one intermediate. Remember that those transition states are where those peaks are, and the intermediate is whatever is made that isn't a product. And so he labeled here products, and he labeled reactants. So we know this has to be an intermediate. And if that's intermediate, our peaks are transition states. So we should say two transition states and one intermediate. Two transition states and one intermediate. The answer is C. Okay. I'm going to start another video for this last part, this open response, so I can open a new page.